Okay, I'm going to make a video here about this problem, and the reason I'm making this problem is because I posted this on my exam, and you guys struggled with it, and I just wanted to make sure that it was clear the correct way to solve it. Okay, so let's begin with two blocks are sliding to the right across a horizontal surface. The mass of block 1, the block behind, is 6 kilograms, and the mass of the block 2 is 3 kilograms. No frictional force acts on block 1, however, kinetic friction force of 6 newtons acts on block 2. Determine the magnitude of the forces with which the blocks push against each other. Okay, so that force between the blocks, okay, it's happening right in here, right? And it's an action-reaction pair. There's force of block 1 on block 2 and block 2 on block 1, and they will be equal but opposite. And hopefully, you should be able to tell just by kind of what I've just kind of talked about here, that the net effect of this, because the only external force in the x direction is to the left. So our expectation would be that the acceleration will also ultimately be to the left. Basically, these blocks are going to be slowing down. Okay, so my expectation for most of you guys is that the way that you would solve this is that you would start thinking about, okay, well, I've got to get at this force, which is between the two blocks. So the only way I can get at that force is by creating a free body diagram of one of the blocks, right? Because if I do the whole thing, F12 is not in there, like it's an internal force. So we want to do just one block. And for no particular reason, although I could give you some very good reasons, but I will start with block 1. Maybe the reasons, I guess, would be block 1 is easier than block 2 because it has no friction on the bottom. And the other reason that I'm going to start with block 1 is I kind of work left to right, so it's just going to kind of be easiest for me. Okay, so the first thing that we're going to do as we analyze these forces is we're going to start by noting that this thing has weight. That is the only field force, the only non-contact force. So we'll have weight going down. I'm going to call it Fg1. Okay, and then other than that, we've got these two sides. So we have to think about what's touching the blocks, right? Because other than that, we have to think about we've got the non-contact force. So now we need to get the contact forces, the surface forces. And these are only happening due to contacts on the right-hand side of the box and the bottom of the box, okay? And those forces have to be normal forces and friction forces, with the normal force being perpendicular to the surface and the friction force being parallel to the surface. So let's start with the bottom, and along the bottom, we're contacting the bottom, so there's a normal force, so that normal force will be up. We'll call that Fn1. And then there will be a friction force along the bottom, except for the fact that this problem very specifically told us no friction force acts on block 1, so therefore we won't bother drawing the friction force. Okay, now we've got this, we've got the right-hand side of this box, and the right-hand side of the box is touching box 2, and so it also has a normal and potentially a friction force, although no one drew the friction force. And I suppose that sentence says no friction force acts on block 1, so perhaps that was correct. But anyway, we'll go ahead and draw it in here just for completeness, and we'll draw the normal force, which I'm going to call F12. Please note that F12 is a normal force, right? That's what's, the definition of the normal force. It's the force that keeps the two surfaces from sliding into each other, right? And so, and note that it has to be a push, right? And I think that should be logical enough that this is a pushing force, because without M2, M1 would not slow down, right? It's just going to keep on going forever at whatever its current velocity is to the right. However, M2 is in front of it, and it is pushing back, and so that's causing this to slow down. So before we get into doing any more free body diagrams or anything like that, or analyzing box 2 or thinking about the system more in depth, I think it would be this is a good time for us to go ahead and analyze what's going on this block, right? So the point of the free body diagram is that I should be able to look at this and ignore the rest of the universe. It looks like I kind of leaving that little diagram up there on the screen, but we don't really want to be thinking about that, right? So the first step always in Newton's laws is we want to do sum of forces in the x or sum of forces in the y. In this particular case, I'm not even going to bother with doing it in the y direction. And you may say, well, why not? Usually we do the y direction first. The reason we won't do the y direction first or even at all is because in this case, usually the reason that we do that is because we are concerned about getting the friction force, and we need to know the normal force first. However, in this case, we have the friction force. We know it's 0. So there's no reason to bother getting the normal force. We don't care about what's going on in the y direction. So we will not do that. So let's just do sum of forces in the x. We always just write that out. And then step 2 is we're going to expand that equation. So we need to look for all the forces in the x direction. If we look at our free body diagram, The only force in the x direction is F12, and it is to the left, right? So it is in the negative x direction. Okay, and then we'll say equals, in place of m, I'll put m1, and we'll just leave that ax as a sub x. I mean, we could change it if we wanted to, but I think we're gonna leave it as a sub x. Okay, so that is a great equation. It's very useful, very helpful for us. However, we must note that it has two unknowns. So it's got F12, which we don't know and we're looking for, and the acceleration in the x direction, which is not given. So a lot of you got to this point and you freaked out. I remember I came to the room, you raised your hand, you said, well, we don't know the acceleration. And what you're supposed to do if you're in it with an equation with two unknowns is you have to come up with another equation. So let's go ahead and come up with another equation, and we'll do that by looking at box 2. Okay, so looking at box 2 is going to be, kind of a rehashing of doing exactly the same thing we just did, except for the fact that, box 2 is a little bit more complicated, right? It's got that friction force on the bottom. So anyway, so just like earlier, we're going to go ahead and think about the forces on it, and we'll start with, the force of gravity, as always. I'm called Fg2, and that's going down. That's my only non-contact force. And then I got to think about the surfaces. And for this one, the surfaces that are touching things are the bottom and the left-hand face of this thing, okay? So on the bottom, we have a normal force going up, which is Fn2. And we've got a friction force, which is given to us, going off to the left of 6 newtons. Okay, cool. Obviously, we're just going to call it F sub F2. Okay. The other surface that we have to deal with is the left-hand side of this box, which is, where this thing is being pushed forward by M1, right? So there's a normal force F12 going forward. And then we've got a friction force also, which is equal but opposite friction force, Newton's third law, which I'll draw for completeness, but we're not really even going to worry about that at all. All right, so just like before, we're going to go in the x direction, and we're not even going to worry about the y direction, because again, even though there is a friction force here, we don't need the normal force to get it because it is already given to us. So let's see. So then, if we look up at our little diagram here, we've got two forces in the x direction. I've got F12 pushing forward, and I've got F force of friction 2 pushing backwards. Okay, so if I combine those, and it equals, in this case, M2 times x, right? Because that's the mass of the smaller box. Okay, so good. So now we've got, if I kind of box these two off, I've got two equations and the exact same two unknowns, which is exactly what I wanted. Okay, so at this point, this is just algebra. So I'll kind of walk you through it. Step by step. Okay, so the first step usually is that we're going to want to, we're going to figure out which one of these two variables we want to get rid of, right? So we've got F12, we've got a sub x. Well, we want to get rid of a sub x because we don't care. The problem didn't ask for a sub x. There are versions of this online where they do ask for a sub x. I just didn't ask for that. So in this case, if you're not asked for it, then you want to get rid of it. So we're going to choose the simpler equation to solve for a sub x in order to plug into the harder equation. In this case, the simpler equation is equation 1. So we will zoom in on that, and we will solve this for a sub x. Well, that's lucky for us. This is really pretty straightforward and easy. Boom, got it. Okay. So a sub x equals negative F12 M1. So that negative implies that this box is decelerating. So it's moving to the right, but it's accelerating to the left. Okay, so it's slowing down. All right, so we'll take that result and we'll go over here and we were going to plug it into this guy. Okay, so we're going to get negative F2 plus F12 equals M2, and in place of a sub x, I'm going to put that result from earlier, which is negative F12 over M1. All right, so the first thing that I'm going to start doing is I'm going to start kind of moving things around. And so I'm going to get F sub F2 equals F sub 1, 2, M2, M1 over F1. And all of those have negative signs on them, so I'm going to go ahead and turn them all into positive signs by just multiplying everything by negative 1. Okay, so now I'll do some quick rearranging. F sub F2 equals F sub 1, 2 times Just kind of pulling it out, 1 plus m2 over m1. And then I'll divide both sides by what's in the parentheses and ends up with an equation for f1, too. Okay, so I'm at this point, and I'm going to go do this fairly quickly, but you plug and chug, and you'll get your final answer. I will note that many of you skip this plug and chug step, and then you get a wrong answer, and I don't know where you got it from, and you lose more points than you should. So please do a better job of including that for me. Thank you. Okay, so now at this point, there's two things that I kind of want to do at the end, okay? And so the first thing I want to do is I want to show you how I would do it, okay? Because this is not how I would have done it, okay? And then the second thing is I want to show you these numbers in actions, okay? Numbers in action. Okay, so these are the two things that I want to do now that this is done. I'm going to show you how I would have done this, which is a little bit quicker and less algebraically intense. This isn't too bad, but nor is it, it's still more work than I would like to do. And it also, there's a point in here where the intuition is just getting lost, right? We're just doing some algebra, and it's kind of like, I don't really get what's going on here. Okay, so what I'm going to do here is I'm going to show you that I would have done this free body diagram right here, free body diagram 1, and then I would have done a different free body diagram. It looks like I forgot to label this one. And I would not have done free body diagram 2. I would have done free body diagram 1, 2. In other words, I would have included both boxes at the same time, and I'll show you why. Okay, so the first reason why is because, it's just easier. And so again, as we consider these two boxes together, we're going to treat them like it's one giant box with a mass of m1 plus m2. And we've got the same sort of force diagrams that we've had before. We've got force of gravity going down, which I'll call FG 1, 2. And then, well, what surfaces? What are the contacts on this thing? So on the bottom of this sucker, right, it's touching the table. And so that means it's got a normal force going off, F sub n 1, 2. And we know the friction force going to the left, which is F sub F2, right? It's only acting on box 2. It's not acting on box 1. So the total friction force is F sub F2. All right, so cool. The nice thing about this particular equation is that if I arrange it that way, and I do the sum of the forces in the x direction, hopefully you can see that we only have one force in the x direction, which is force of friction 2. We've got a mass of m1 plus m2, and then we've got a sub x. And what's great about this is an equation with only one unknown, and it's one of the two unknowns that we had. So if you were able to see this, and no one did, but if you're able to see this, then you can solve for the acceleration very, very easily. So with a little plug and chug, you can see that the acceleration in this case is negative 2/3 of a meter per second squared. Okay, so we'll take that value, and what I would have done is I would have plugged it into my result from free body diagram 1. And if we do that, let's just kind of walk through it. Okay, so we'll go over here, and oh, look, there it is right there all set up for us. We're actually going to look at this version of the equation, right? We're not going to do the other one. And if we plug in our acceleration from earlier, we will end up with, let's see, negative F12 equals m1 is 6 kilograms and negative 2/3 of a meter per second squared, and F12 equals 4 newtons. Okay, so I just find that to be easier way to solve this than the longer algebraic way that we had done to the right. Okay, so I'm going to show you one other thing that I think is really powerful for you guys to be aware of. And it's the fact that you probably think, oh, well, look, we could have had an extra unknown. We have 3 equations here. We've got equation 1, we've got equation 2, and we had equation 3 when we did the whole system. And I wanted to point out that we do not actually have 3 equations. We actually have, we have 3 equations, but they're not what we would call independent. So what I mean by that, and this is heady stuff for a high school class, right? But if we look at all 3 of our equations, so this is equation 1. It came from, the free body diagram of box 1. This is equation 2, and it came from the free body diagram of box 2. This is equation 3. It came from the free body diagram of box 1 and 2 together. Now, and hopefully this makes a little bit of logical sense to you, but I want you to note, because I'm trying to get at whether or not these are independent, but look at if I add these equations. If I add equation 1 to equation 2, right, please note that what will happen as I add them is that, let's see here, so I've got a negative f12 and a positive f12, and so those cancel each other, and I'm left with negative f sub f2. Okay, and then on the right-hand side, let's see here, I got m1 times ax, and I got m2 plus ax. So if I add those up, I get m1 plus m2 a sub x. So in other words, this third equation, which came from the free body diagram of both of them together, right, it is a linear combination of the other two. So it is not an independent equation. Okay, which means, and this is heady stuff for high school class, but basically, you know, it doesn't have any new information for us. Okay. Anyway, I thought that was kind of interesting. In a second, you know, when we start the new semester, we will be doing bridges. When we do that, keep in mind that there's like a lot of subparts of the bridge as we work together, but all the subparts, if you add them all up, you'll get the equation for the total bridge, which is kind of cool. So, all right. Well, I hope this was helpful, and I hope you guys had a lovely break. Okay. Goodbye.